Hi, welcome back. Today I am going to talk about Fourier Bessel series. This is a part of a course PH3103 at IISER Calcutta. This is an interesting topic need to be covered because here is a smart techniques used to convert seemingly impossible Stern-Liouville problem into a possible Stern-Liouville problem. Offhand, it looks like that Bessel functions will not come under Stern-Liouville boundary conditions and cannot be used as a basis function. But with smart tricks, we are able to do it, and it gives you also a deeper insight into the Stern-Liouville boundary conditions and usage of orthonormal functions. Let's jump to it and go on. Before we get into Fourier Bessel series, first look at the one of the important properties of Bessel function, that is we need to know roots of the Bessel function. Let's pay more attention to the roots of the Bessel function. For this, let's compare it with the roots of the sine and cos function, which we understand well. The basis function for the Fourier series, that is sine and cos functions, are periodic functions, and they have roots also at the periodic interval, and these roots can be used for satisfying the Stern-Liouville boundary condition, especially the Dirichlet boundary condition, for which the function value itself goes to 0 on the boundary. When the interval is from minus L to plus 1, we can map that to minus pi to plus pi, and went on with the satisfying the Stern-Liouville boundary condition. When coming to Legendre polynomial, we did not have much problem because it naturally satisfies the Stern-Liouville boundary condition, because p of x there had a value of 0 on the boundary, and we use the expansion around x is equal to 0. In the earlier lecture, from the plots of Bessel function, we have seen that the roots of Bessel functions are not equally distributed, and they are spread all over, unlike the sine and cos function. Let us look at them a little more carefully, and let's get the exact values of various roots of Bessel function for various orders to see if we can make something out. In this case, nth root of Bessel function of order nu is represented by x nu n. That is, nth root of function j nu of x is denoted by x nu n. Let's first look at the roots of the j0, that is x0 n's. The x01 is a first root, which is around at 2.404. That is x01. That is a first root of Bessel function of order 0. And the second root of j0 is at 5.520. And the third root coming at around 8.653. There don't seems to be any relation here, and these roots have to be numerically evaluated using the computer, and often most of the computational or engineering apps provide the function which provides the root of Bessel function, be it MATLAB, Mathematica, or Maple. Any of these would provide you the roots of a Bessel function because it has importance in the boundary value problems. Let's quickly look at the roots of the Bessel function 1, that is the x11, that is the first root of a Bessel function j1, which is at 3.813, and second root of j1 is at 7.015. We can go on like this. We can get j2 and take the first root, and then j2 is the second root. We are looking at the roots in the 0 to 10. We can list all the roots, and then we have j3, which has one root at 6 point something. So these are the root. Apparently there is no relation or no meaningful relation between the one root to another root, unlike sine and cosine, which have roots at the regular interval. Now, how does play a significant role in the boundary value problem? Let's compare the sine and jm And what we have is a Fourier series, f of x, a function is represented in terms of a sine. A I have taken to be 1 for the simplicity. Now let's look at the plot of the function sine n pi x by a, where n is equal to 1. It starts at x is equal to 0, where you have a first root, and next root is at 1, because we have scaled it such that these roots are on the boundary, because then it is easier to follow the Stern-Liouville boundary condition, especially the Dirichlet boundary condition, where the value of the function goes to 0, and we have a half cycle in our interval. Now for n is equal to 2, we have sine 2 pi x by a. Again, we see that the first root is at x is equal to 0. That happens for all the sine n pi x a. And then we have a one root in between, and the second root on the boundary x is equal to a. In this case, it is 1. Now here we have totally 3 root and 1 in between, and we have a one full cycle of sine omega t. Now when we go to n is equal to 3, we have 3 pi x by a. Now again, it starts root at x is equal to 0, and its end with the root at x is equal to a, or x is equal to pi. Again, we have 2 root here in between, and then we can go on like this. Many n root you will have. What is important to notice here is that, again, when you plot them all together, there don't seems to be any relation, because you can see root at some scattered point here, and you mark them all, they would be essentially distributed all over. On the boundary, they do satisfy the Stern-Liouville boundary condition. That is, conveniently, we have mapped them. Now, there is an alternative interpretation of this. Let's look at the function sine pi x by a only. Now let's take only one cycle. Now if we take only one cycle, it would start from x is equal to 0, and then it will go all the way till x is equal to 1. So this is our interval, and then what we do here is that we take this interval and map it to an interval from 0 to 1. Of course, in this case, we are mapping the interval from 0 to a to 0 to a. So it is an identity mapping, and you have a one cycle which is mapped onto the same thing even after the transformation, and you see that it satisfies the boundary condition. Now let's take an interval from 0 to 2a. Then we have a full one cycle. Now what we do is we take this interval 0 to 2a and then map it to interval 0 to a. Now we see that the entire cycle is shrunk, and then we have again zeros on the boundary, and then we have one cycle inside, and that is all mapped into 0 to a, nicely satisfying the Stern-Liouville boundary condition. Now we go ahead, we take an interval from 0 to 3a and plot the same function sine pi x by a. Now we map this interval from 0 to 3a to 0 to a. Then we see nicely that it would correspond to similar, it would look like sine 3 pi x by a. So this is a scaling or mapping such that the frequency is increased by taking many cycles. So we can do it two ways. We can take the same function several cycles, or we can take a higher and higher frequency and fix it to the one interval. And then we can take the next one too. We can take a Fourier interval and then map it. Again, you will see we have nicely reproduced the plot earlier shown, which has sine n pi x by a in the interval 0 to a, which acts as a basis for the orthonormal function because it nicely satisfies the Stern-Liouville boundary condition. All we have done is we have taken the function sine pi x by a in the interval a, 2a, 3a, 4a. These are the roots corresponding to the function sine pi x by a, and then mapped into the interval 0 to a. And that gave us many cycles and naturally satisfying the Stern-Liouville boundary condition. Now we can use the same trick for the Bessel function. The Bessel function, as you see that the roots are not at the regular interval, we see that that doesn't matter as long as we can manipulate them properly and scale them and rearrange them properly. Here I have shown only J0 function. As we have seen that the higher order is not important, we can do the entire thing using the J0 itself by mapping the roots to a fixed interval 0 to a. But in the sine omega t, nth cycle of the sine pi xa is when mapped to an interval 0 to a becomes exactly equal to sine n pi x by a. Now, may not happen for the Bessel function. So you have various orders of Bessel function, and it can be done for each orders in Bessel function. For example, you take the J0 function, you have various roots, and you map all the roots to a fixed interval between 0 to a, and then they would be satisfying the Stern-Liouville boundary condition, and you can use them as your basis function. Let's do it explicitly. Let's take here on the outlet, you have a Bessel J0 function, which goes all the way from some cycles. And inside this inlet, which has been mapped to an interval 0 to a, where a is equal to 1. So we are mapping various cycles of Bessel function to an interval 0 to a, where a is 1 in this case. We can see that the first root of Bessel function at this point, which will be mapped to 1 here. Now we see that the root of Bessel function x01 is a map to an interval to a such that it is scaled x0j x by a. I used j here instead of 1 because it is done for all the roots. So I didn't want to change it because otherwise it become cumbersome. And this arrow is also shifted a little bit because this 0 is here. In the next plot it will be all right. So we have a second root which is again mapped into the interval 0 to a. In the first case you had a half a cycle, not necessarily as symmetric as a sine omega t. And then in the second scaling, we have a second root is when it mapped to 0 to a, we have one full cycle. Again, it is not symmetric, but it has all the ingredient. It does become 0 at the value x is equal to a. And then we take the third root, that is x03, and then we have a 1.5 cycle, which is again mapped into interval 0 to a, and again it nicely satisfies x is equal to 0. Again, this plot is not as symmetric as sine omega t because their roots are not at the regular interval. If the roots were at the regular interval, probably they would have looked very similar, except that some of the scaling is slightly different. Now, let's take next root, that is at x is equal to 0,4, that again mapped to a, and then you can see there is a full 2 cycle in there. And then we can go to the next root, that is x05, that is a fifth root of Bessel function J0, and then you can see 2.5 cycles there. So when you do this arrangement, at least at this end, Stern-Liouville problems are naturally satisfied. At this value, the function takes the value of 1. Then we will look at the differential equation. With this arrangement, we will see if we can satisfy the Stern-Liouville boundary condition and express the L2 functions in terms of Bessel function. This would be useful when you have a cylindrical coordinate and where we can solve the problems using this method. Now, there is nothing sacred about J0. In this I have used, you can use the higher order Bessel function, same approach would do, and then you can map them to the fixed interval and use them as a orthonormal basis. So this idea is again called the Fourier Bessel series. We have seen Fourier Legendre series. In the similar way, we express the L2 function in terms of Bessel function. Now we discuss briefly about the Bessel function as an orthonormal function. Let's start with the Bessel ordinary differential equation. This is given by x square d square y by dx square x into dy by dx plus x square minus nu square y is equal to 0 we know that the general solution is a Bessel function of the order J nu. Now we can take an arbitrary interval in which we want to express the Stern-Liouville orthonormal functions. Now you note that from the physical application point of view, our r coordinate in the cylindrical coordinate is transformed by multiplying by the k. K is the eigenfunction corresponding to the z part of the equation, and then we have a x is equal to k times r. Then that scaling have to be kept in mind when we use x here in terms of the physical application, and the cylindrical coordinate, it is always k into r. Even though we say it is a function of r, it is actually k times function of r. Equation here looks like 1 by r d by dr of r into dy by dr minus nu square by r square into y minus k square into y. So this is written such that it looks like an eigenvalue problem for the differential operator written in terms of a Stern-Liouville form or the self-adjoint form. Now you see that there is a slight difference here. There is a function here which we have not seen in the earlier case. We have always had a differential equation of the form d by dx of some p of x dy by dx minus nu square x square by y. So this p is r itself, and we have an additional function 1 by r multiplied by to the whole term, and we can take care of it. That is often called the weight function in the orthonormal function. You can weigh the dot product with respect to a weight function, and that can be easily incorporated in terms of this. And we know the solution of this differential equation is a Bessel function and Newman function, and we have seen that these two are set of linearly independent functions for Bessel differential equation. Of course, we have to worry when 0 is in our domain. We cannot use Newman function, otherwise this should do. Now, in terms of Stern-Liouville differential equation, we write this as 1 by w of r d by dr of p of r d by dr of y plus q of r y is equal to minus lambda times the y. So this is a general form of a Stern-Liouville problem with the weight function w. So let's look at it in more detail. So what we have, p of r is a standard form. This should have been small. And then we have eigenvalue lambda here, which is essentially a constant coming out when you operate on the differential equation. And then we have this weightage function, which could be a function of r. And that can be incorporated very easily in the Stern-Liouville boundary condition. Let us remind ourselves that the Stern-Liouville boundary condition between R1 and R2 is given as a P of R y1 into y2 prime minus y1 prime into y2 evaluated at R1 and R2 is equal to 0. We have seen in earlier case P of R is equal to 0, or we will have to satisfy this boundary condition. Let's see how does the Bessel function does this trick. Now it is interesting that one would not have expected this to happen. Now two tricks which we are essentially using here. One is a scaling. We are scaling the roots of Bessel function at the fixed interval 0 to a, such that all the roots are mapped back to x is equal to a. Now that would satisfy Stern-Liouville boundary condition at one end. But we have seen that at r is equal to 0, then we got to check this too. At r is equal to 0, there seems to be a peculiar coincidence. P of r here is exactly equal to r, and that is equal to 0, and then it satisfies the Stern-Liouville boundary condition at this point, and this is at the other boundary. We can have y is equal to 0. At r is equal to r2, we can map all the roots of Bessel function to r2, a fixed number, and then we can satisfy the Dirichlet boundary condition. solutions of Bessel functions can be, if the different eigenvalues can be used as orthonormal functions to express L2 function. So here we take R2 equal to a positive number, and map all the zeros of Bessel function x nu n, the nth root of j nu, map to x is equal to a, such that Bessel function argument is scaled x nu n k of r by a. When k of r becomes a, it becomes hit the root of a Bessel function, and we satisfy the Stern-Liouville boundary condition, and we can express any function in terms of this by using this mechanism. So this is an interesting mechanism, but we see that it is orthogonal, not orthonormal. We got to normalize it in the interval 0 to a. That can be easily done using the identity or the recurrence relations of Bessel function. It is simple to remember actually. Integral from 0 to a x, the weight factor comes into here. You can also see that it is a Jacobian for the cylindrical coordinate, because we are using integration has to always come with the Jacobian, and we can physically see the weight function plays the role of Jacobian in the integral, and integral 0 to a x of j nu x nu x into x by a square is equal to a square by 2 j nu plus 1, that one order becomes more. So nu n is a root of j nu, not root of j nu plus 1. So we can have this non-zero. So this is what we have is a normalizing factor j nu plus 1 of x nu n. This is how we use the Fourier Bessel series. We can have any L2 function in the interval 0 to a for some positive real number a. Then we can express it in terms of the Fourier Bessel series as f of x as n going from 1 to infinity, b nu n, that is a coefficient, j nu of x nu n of x by a, such that the roots are mapped, and the Fourier Bessel coefficient b nu n is given as a bn is equal to 2 by a j nu plus 1 x nu n whole square into integral 0 to a x, the weight factor, f of x, the function, and the basis function, that is j nu x nu n x by a of dx. So here you see that we are expressing everything in terms of the j nu, that is only one Bessel function is used. You can use j0, then the nu will be 0 in all the things. So there is j1 does not come anywhere into picture. There is no secret about using any specific Bessel function. You can use j0, j1, and for each you can obtain a series expansion. Again, it depends on the convenience, what you want to do, whether you want the function to be 0 at x is equal to 0 or not. If the function is non-zero at x is equal to 0, then it is better to use a j0 as your basis function. If it is 0 at x is equal to 0, then it is better to use any of j1 or any of higher order Bessel function to expand in terms of Fourier Bessel function. Of course, we have to do this integration. It may often turns out to be non-trivial to do this integral, but that is what is the part of game.